Hello and welcome to my presentation of hierarchical multi-level electric power system simulation with smart photovoltaic systems using the functional Mockup interface on the Lawrencium computing cluster. My name is Christoph Gehbauer and I conducted this work together with my colleague Joshua Müller. So a little bit an overview of what you will hear in the next 15 minutes. At first I will introduce the project team. Then I will speak a little bit to the functional Markup interface, which is especially relevant for the ones not familiar with this standard. More specifically, I will talk about functional Markup interface for the power systems industry, which is the center of our research. And then this larger chapter here with the simulation setup and results, and then speak a little bit about future research and outlook on this platform. Hello, everybody again. My name is Christoph Gehbauer. I'm the principal investigator on this project, and I'm a principal scientific engineer here at the Lawrence National Laboratory. And I conducted this work together with my colleague Joshua Müller, who is a scientific engineer also here at the lab. So at first, I want to introduce the functional Markup interface, which is really an industry standard for co-simulation. It originated in the European automotive industry, where the desire to link different components of vehicles on a common platform and simulate them together was really the driver for this development. And so the way how it works, it basically exposes standardized interfaces to input data into a simulation model and to get data from a simulation model. And the way how it works is that, so you can see here in this on this image here on the left, for example, an electric circuit or a control, which can be exported into a functional Mockup unit, which is the exported simulation model using the FMI standard. And this functional Mockup unit is basically it's a zip file, which includes compiled C code for execution of the model. So basically, the model is translated into a set of C functions, which are on the outset they're predefined with the functional Mockup interface. This zip file also includes an XML file which describes the model inputs, model outputs, parameters, dependencies, and so on. And different models can be exported using this interface into an FMU, and then these FMUs can be linked together in various ways. And there are two different ways of exporting a model or compiling such a model. So the one mode would be the model exchange mode, where the derivatives of the model are exposed, but the solver is kind of external to the model. So it needs a global orchestrator to execute the model. The advantage is that it can really make use of variable time step solvers which roll back in time, since the integration happens outside of the model. The other way is the co-simulation export, where the solver is actually included into the model. So there is no need of external solver, so it's a little bit easier to share the model or to link with the model, but it has the disadvantage that it's not really possible to roll back time. So some of the advantages we get from the model exchange FMU. Generally, it's a widely adopted standard by industry. It's currently supported by more than 100 simulation tools, which either support the export of the simulation model as an FMU or the input or both. And one important piece which we really rely on in this paper is this package which was developed here at the lab called Simulated to FMU, which allows to export Python code, which is very widely used in research environment, and export Python code as a functional Mockup unit. So far it supports both modes, so it supports the model exchange and the co-simulation mode, but there are some limitations I will speak about in a second here. And then more specifically, we developed we want to introduce the functional Mockup interface for the power systems industry. We had a large project here at the lab called Cyber-Physical Co-Simulation Platform for Distributed Energy Resources in Smart Grids, code short SCooDER. And so here we really wanted to leverage this standard. So you can see here that through this FMI standard, we were able to couple multiple different simulators. And one typical problem in the power systems industry is always the distribution and transmission grid, which are usually different domains or different simulators, basically with different expertise. And with this platform, for example, we were able to couple SAM, which is a really common distribution system simulator, with GridDyne as a transmission simulator. But not only these two simulators, we were able to extend basically a library of various different FMUs, which were coupled in various different ways through the SCooDER platform. So this included, for example, real-time sensor data. It included EVs and EV charging data. It included PV and smart inverter, advanced control systems. And we were also able to interface with a real-time simulator. And if you're interested to learn more, I put 2 papers on the bottom here. Okay, let's speak a little bit about the specific simulation setup here for this paper. So our main objective here was really to demonstrate SCooDER, the SCooDER platform, and the functional Mockup industry to be applicable for the power systems industry and feasible in terms of simulation. So what we did, we coupled more than 80,000 individual simulators, so individual FMUs, which are at the end representing of the whole US state's electricity grid. So with a scale factor of, so at the end it scales to around 4 million customers. So it's not a huge state, but it's in terms of its topology, it represents a whole state. So we distributed the simulation across multiple compute nodes at LBNL's Lawrencium high-performance computing facility. We executed the simulation for over 1 day period, so for 24 hours. It did use a variable time step solver. However, we only had an hourly load change. So at the end, it's basically an hourly profile. And then we evaluated the feasibility and necessary computational resources. I will speak about in a second. So for our electric grid, we had the following setup here, where we used for transmission, we used, so all of them are example feeder networks which are widely available. And so for transmission, we used the IEEE 57 transmission system, which where we utilized 42 buses. We used the SCooDER medium voltage distribution system, and we used the Kerber low voltage distribution system. So the way how these different networks are coupled are that, so this Kerber network is a 146 bus network, and this is coupled to the medium voltage distribution system here on each of the 13 buses. So basically the Kerber network is duplicated 13 times and connected to all the buses, to each bus of the SCooDER network. And then again, the SCooDER network is duplicated 42 times and connected to the 42 buses of the IEEE 57 network here. So this ends up to be around the 80,000 customers I was talking about before. And so each customer is modeled with a time-varying load profile, PV generation, and smart inverter. And for the ones not familiar with smart inverters, so smart inverters in this case are devices which can regulate their reactive power output to basically interfere and regulate the local system voltage at the point of common coupling. So basically, it's a reactive power, or Q, as a function of voltage. There is some saturation, where in this case we set it to 5% of the voltage. So basically, it saturates at 95% and 105% to keep the voltage within those bounds. But there is a very tight coupling between Q and V. So that's one challenge here for the simulation setup. And then we randomly assigned the DOE typical load profiles to the various nodes of the 146 bus network, actually throughout the whole network. And we use a custom distribution, which is based on PG&E feeder data. So you can see here on the lower left, we got 50 PG&E feeders. So PG&E is the the local utility company here for Northern California. So we got 50 feeder data, and we assigned, based on the distribution in their feeders, we assigned customers from the DOE load profiles to the low voltage network. And then in order to allow parallelization, where in this case we used 12 Lawrencium compute nodes, which adds up to 384 cores, CPU cores, we did the modification to the simulator to FMU wrapper, where you can see it illustrated here on the right, where normally, so here's the feeder model FMU. So this one would be the FMU exported through simulator to FMU. And in this FMU, you have a Python code. So normally in this case would be the PandaPower wrapper. So we use PandaPower for our power system simulation. It's a Python tool, or it's possible to interface through Python. So normally it would be all kind of contained within this FMU. But in our case, since we want to run it on various different nodes and in parallel, we came up with this architecture where the actual FMU just includes some code to interface with a web server through HTTP and JSON commands. And then on the other hand, each CPU core basically runs one server, which again then hosts the actual wrapper or actual code. So we kind of took it out of the FMU into a standalone web server where the FMU communicates kind of on the back end with the server. And also in addition to allow the parallelization, we did some additional modifications here to allow re-execution of multiple networks in parallel. And then to be a little bit more specific with our architecture, so you can see here the PV FMU in green, which is a model exchange FMU. We have the 146 smart inverter FMUs, and we have the feeder FMU. And then all those are coupled with through PyFMI with a variable time step solver. And then this whole network is again duplicated 13 times and coupled with a custom orchestrator with a fixed time step solver. And then this coupled distribution FMU is once again duplicated 42 times and coupled with another custom orchestrator into transmission FMU. All the models communicate with each other through an exchange of voltage at the feeder head and return of active and reactive power at the feeder head. So that's the same for all of those, except of course here with the smart inverter, we only have the reactive power. And then to the results, so you can see here on the right, the upper plot is the distribution of loads across all the 80,000 customers. So we got some distribution even if we only use the limited set of the DOE load profiles. You can see the PV generation on the secondary axis. Then we can see the control action of the smart inverters here, the reactive power, which ranges from 1 to -1 per unit. And we can see there is a wide variety based on the voltages. So in the third subplot here, we can see the voltages mainly stayed within the bounds we defined, within the 5% bounds. But there were some cases where even with the reactive power control, it was not able to keep the voltage within that bound. And in terms of solving time, so most feeders only took around 10 iterations to solve, so they were really fast. But there were always few which took much longer, so in the order of 300 iterations, which added up to around 800 seconds per iteration of CPU time. And this is not one time step iteration, but just one iteration within the system. So these were conducted multiple times to finally converge. And then a little bit to the outlook. So the simulator to FMU currently does not include state events. So we are hoping to add the capability of passing state events through different structures or different hierarchies to at the end propagate things like switching events and faults, which currently would not happen. So right now, it would, all the state events would just stay at the feeder level, and then in the next time step, so in this case it's an hourly time step, so in the next hour it would propagate to the higher level hierarchy. So obviously that's not optimal, and that could be easily solved by adding state events to simulator to FMU, but adding these events is not that straightforward. So that's something we're still working on. Then, of course, advanced orchestrators to handle model exchange FMUs. I mentioned before, we use the co-simulation FMUs on the higher hierarchy levels, which also has to do with the state event handling. So that's definitely one improvement we want to do. Validating the results would be really good, but obviously difficult to get data for so many customers. But on the other hand, we did validate the individual models either in software, or actually some of the models like the inverter controller and PV generator. We actually validated our test facility here at LBNL. And then the ultimate goal would be, of course, for this platform to be useful for example, ISO operations, where different scenarios could be explored in a like day ahead or hour ahead scenarios. And then this platform can also be used to develop and evaluate new control schemes by having a really high level of detail. But overall, we were able to show that the FMI standard is applicable for the power systems industry, and we coupled various simulators with through the FMI standard, and we're successfully able to solve the system. And that's it. I added a few links here in case you're interested. Other than this, if you have any questions, then see you in the Q&A session in a bit. Thank you very much for your attention. Have a great day.